Welcome back, everyone, and today we are at our first big milestone, or actually second milestone, to deal with our inverse kinematic system. And what I have on screen right now is a project for Unity where this guy kind of put together a random dance, and it looks pretty cool how he did it. So it's just really just moving things randomly and using purling noise, and then feeding that information into the Unity IK system, and that's how he was able to generate this procedural random dance. And then you have settings and everything else. So we're going to actually build this a slimmed down version of this, because there's a lot of like bits of randomness and noise. He put it everywhere. Like the head movement has noise. I'm not going to do that, but how you do the arms is the same way you kind of do how you do the head and certain things like that. So we're just going to focus on the main body parts and just build something simple and bare bones, and anyone can then, once you know how the whole procedural dance works, then it's easy kind of just implement more pieces to it and go full crazy with how he did it. So we're going to build all this in WebGL and JavaScript using the IK system and fungi that we've been building for the past 2 years. So, all right. So we're going to focus. This is going to be broken down to two parts. Let me just put this here. This first video, we're going to deal with foot movement, and hip movement. So we're just going to focus on hip and feet. And the next video, we'll focus on the spine and hand movements. So this way we can, really can not mess up, but really just play around with it. So I'm trying to make these videos short, but this is kind of a complicated thing. So let's get straight into the source code. All right. So we got our usual fare, and we're going to use the Vegeta mesh today. Right now I have the skin part turned off, so we're going to only see the skeleton, and I'll turn on the skin in the end. All right, so the first thing, like I said, we're building a procedural animation, right? So one of the first things I learned when I was going through the guy's code, I can't say his name properly, the great Unity guy. First thing you got to do is set up a cycle, an animation cycle. So if you look at like a timeline and like you have like 4 keyframes, your entire like animation cycles from start to finish, and then you loop over the animation again. So we're trying to create a single cycle of animation and then loop over. But the thing is, every cycle we're actually applying extra random and purl and noise. So even though we're not repeating the same steps over and over again, we're actually moving in different places. But we still need that cycle of animation to kind of keep us moving forward. Especially with purl and noise, you need a constant value moving in the forward direction. So that's what this helps us with. So first thing, I create like a very simple class called number cycle, which just a number, how fast I want to go per second, like just a constant increment of a number. So like right here, I say like for default, I want to go 0.2. That's I want to for every second of animation, I want to go from 0 to 0.2 to 0.4 to 0.6, and that's it. And that value I can actually use to actually control the speed of the animation. I can actually slow it down or speed it up. So we'll play around with that a little bit later. So, but like I said, that's all it does, and it has just 2 functions into it. Give me the floor and give me the fraction. So for every cycle, for every complete cycle, we'll have, by using the frac function, which gives us fraction, will give us basically the normalized value between 0 and 1. So this way, when we're doing a lot of certain things with the animation, like moving the hip up and down or whatever, we have a range of how much we want the hip to move. By using the frac, we go from 0 to 1 and back to 0 or whatever, however we need it to go. A floor basically gives us the floor of the value. So let's say if we're on our first cycle, the floor will be 0. If we're on a second cycle, the floor will be 1. And this actually allows us to use it to help control our feet movement. Because this way, once we know what the floor is, we can actually just do some bitwise operations, and we can just alternate between 0 and 1. So instead of using a modulus that normally people would use, we can use a bitwise operator, which is less costly than a modulus, and just alternate between 0 and 1. Because the one of the things that we have to realize, like, or when you that when you dance, especially how his example works, is that for every time you alternate, there's one foot on the floor, and that foot on the floor, it becomes the pivot, and that pivot is what you kind of rotate around. So one whole cycle of animation is having one foot raise up and then come back down, and then the next cycle, the other foot goes up and comes back down. So that's what we're building here. We're building a cycle of movement between our feet. All right, so and by using floor allows us to do that. Like I said, it's just like same thing as saying x modulus of I think 1, or is it 2? I keep forgetting. So this we always just at the end of every cycle we just very easily alternate with mathematically without actually keeping track or without doing if statements or anything like that. So no if statements, no modulus. So we're going to do it. All right. So I have like a smooth step function. It just smooths out between 0 and 1. So instead of being linear, we can apply more of a curve to our fract function. So this way, like I said, we don't do linear movement. We curve our movement to make it a little bit more smoother. So it slows. It's slow to start, speeds up, and then slows down near the end. So it becomes a nice smooth, kind of like a sine wave, basically. So we're like a sine wave without using a sine wave, essentially. That's where we're going to be curving our values. To start with, we're going to have a lot of configuration values because there's a lot that we need to deal with. So to start off with, we're going to save a reference to our armature. Then we want a reference back to the bone of our hip, so we can actually move the bone of our hip bone in the armature. Then we set up our leg IK chains. So this way we have a chain that we're going to be modifying. Like I said, we're going to be doing IK. This is an inverse kinematics type of thing that we're putting together. Trying to not say ums too much because someone recently talked about that recently. All right, so we're going to create our cycle. This cycle I set it to 0.5, so that's how big our cycle is. Let's see. We're going to choose our hip height, because I don't want to use the exact height of the hip because that means the knee will always straighten out completely. It looks funky. So I set it up for like 0.09 as the maximum height that the hip should go to. And then hip movement is how far the hip should travel down. So the hip is going to be going up and down. So we can always change the distance from the hip height, and then the hip movement is like a subtraction of that hip maximum height. We're going to keep track of which index is pivoting, and we have 2 indexes. So we have 0 and 1. Especially when it comes to this part, we keep track of the position of each foot, or at least not necessarily. We're not keeping a track of each position of each foot. We're tracking the end effector for each foot. So, like I said, this is inverse kinematics. So we're not really moving the feet. We're actually defining the end effector for the feet and arms, and then we just move those around. And then we tell the IK system saying, here, you need to reach this point. So that's what we're doing. So we're alternating between 2 end effectors for the feet. This also, we're going to define how much of rotation. So once one foot's on the ground and the other foot lifts up, your body rotates. In the original Unity example, the guy did like Perlin noise, and he alternated back and forth like randomly. So this way you rotate to the left or you rotate to the right, and a lot of things like that. To keep this simple, I'm just going to rotate in one direction. I'm not going to do Perlin noise. I'm not going to do random random back and forth. None of that. You can add that later if you guys want for yourselves. But like I said, I want to keep this simple. So just simple rotation. Once you see how the rotation works, then it's easy to kind of just tack on extra things to it. So we're just going to keep rotating in one direction, and we're going to rotate. One complete cycle is going to be 120 degrees of rotation. So that's how much it's going to spin, the character. We're going to have the step height and how far the foot's going to raise from the ground. So just like, it's kind of hard to probably see this one. Those are the only images he has. the feet raise up from the ground. For like this example, he probably has it set for really low, so it doesn't raise up from the ground. But that's our setting for that thing. Oh, don't need that. So, and distance is how much distance apart the 2 feet are. So now the interesting thing about how this thing actually works is that you keep a constant distance of the feet. So the feet don't actually move too far to the left or too far to the right. They always stay the same amount of distance. No matter how you move them, they're always stuck in the same amount of distance. So it's always like a perfect radius, or not radius, but yeah, basically a radius from the hip. So it's a radius distance from the hip. So that's another thing we have to set up. Like I said, this is what the Unity guy did, and it makes sense when you start putting it all together. It makes life easier to control where everything else. So how far the 2 feet are going to be, as opposed like in relations to the hip, how far up the foot's going to raise, what angle of rotation that you do as you take a step. And as you can see, I take the foot distance, I divide by half, because the armature is center, so the hip is a center. So 1 foot goes half of the max distance, and the other foot goes half of the other distance. Now we have frame state. This is the values that I'm gonna save to basically do the IK. So this is the IK values that I'm going to be using for the hip. This is where I'm going to save the values. So these are just the frame state for the end effectors. So this is kind of like all the settings to define how the feet are going to move, and this is all the settings I need to define how the hip is going to move. And like I said, and here's where we're going to save the final results before we apply our IK. So the next thing we have is our update function. So every time we have a frame, we call the update function, and we move the step clock forward. And then the first thing we're going to do, we're just going to calculate where the end effector of the feet are going to be. So for right now, we're going to just grab floor. We don't even need that right now. But right now, we're just going to define our P index and our M index. P, anything I put like probably P in front of it, that means to pivot, and M means move. So 1 foot's going to be pivoting and 1 foot's going to be moving. So right now, 1 foot's going to be at the pivot and the other foot's going to be moving. So it's going to actually move. So we're going to get our T step. So we're going to get the fraction of the current state of our cycle. So like I said, it's going to be a value between 0 and 1. And then we're going to take that T step, multiply it by pi, and then make a sine wave. So we're actually going to convert this value into a sine wave. So this way we can really smooth out the movement. And on top of that, we're doing pi instead of pi square. You know what? Let me before I do it this way, let me do this way. I didn't come in to think about it. So let's start off without pi and just do T step. We don't do sine wave. Let's just see how this works. All right, so we're just going to do T step times our height. So we're just going to focus on that for now. So once we have our height, we're going to take let's see, our moving foot. We're going to subtract. We're going to set the moving foot to let's see. So we're going to subtract the moving foot from the pivot foot. So we want to know how far. What is the distance between the two? Currently, like I said, we're moving we're moving the foot that's moving. How far? Like what is the direction? That's probably what I should say. What is the direction from left foot to right foot, essentially? So what direction is it? So once we know the direction, then we normalize it. We have a unit vector. So now we know the direction from our pivot foot to our moving foot, because like I said, the foot is moving. It's moving in a circle and it's moving up and down. So once we have it normalized, like I said, we have a normalized. We're going to rotate it. We're going to rotate that direction. We're going to rotate it by that step angle. So we have a unit vector, we're rotating it. Since it's a unit vector, we need to keep the feet the same amount of distance. So once we have the foot, we then multiply by our feet distance, so that our unit vector now becomes a length vector, or just a regular vector. So now that's a length vector, then we add it to our pivot position. So like I said, the foot that's moving will always be the same amount of distance away from the pivot foot. And then we set the height. The height is then the one that we're actually calculating, so that we're going to move the foot up, we're going to move the foot up, and then we're going to move the foot down. And that completes our first full animation cycle, and then rinse and repeat. And then we do debugging. So if I load this up, so that's what we're doing right now. The red dot is our pivot foot, whoa, and our green dot is our moving foot. So it just, the height is just moving, it's just going linear straight up. But now we want it to go up and then down. So the simplest way, really, is to use a sine wave, and we're going to go by pi. So pi, if we use sine wave with pi, from when we do a sine wave of pi from 0 to pi, we actually traverse 0 to 1 back to 0 again. So this allows us to remap. I probably have it over here commented, which I can't see. It helps us remap a gradient of 0 to 1 into a gradient of 0, 1, 0. So this is where we go. So this is what allows us to go up and then back down, and within one cycle. So it's a remapping. And then it smooths it out too, because it does it. So if I refresh, and there you go. Red is our pivot, and the green is our moving. So now it's moving. It's nice and circular. All right, so we got that. So now we need to alternate. So we need to start alternating our feet, because now we're just constantly moving the same foot over and over again. So now we're going to alternate based on step. So we have our end step. So we're going to say end step. Trying to think. Bitwise 1. So this will give us a value. Any value that's, let's see. Any value that's odd will give us a value of 1, and any value that's even will give you a value of 0. And why is that? Well, if you know binary, then you know the first bit is the value of 1. So if we're going to do an ampersand, a bitwise AND operation, that means when we're using 1 as a mask, essentially, this means only give me all the bits that are all equal to 1. So if it's an odd number, so let's say binary of like this, right? That's 0. And this is a value of 1. And this is a value of 2. And this is a value of 3. That's 3. So that's 0. That's 1. That's 2. That's 3. So our step clock, especially floor, we're for every cycle it's gonna go up on one number by using the floor function. And in case you don't remember what the floor function looks like, all it is just the math floor on the actual value. Okay, so by using that ampersand, we're basically saying we want to say compare this to this and only give me things that are equal to only 1. So the first bit here and here, they're 1 and 0, so they're not equal. All those are equal to 0, so they stay 0. We only want things that are 1 equal 1, 1 and 1. So this one gives us 0, 0, gives a value of 0. So if we apply the same mask here, so we have 1 and 1, well, that gives us 1. And then we have nothing but zeros again. Now we go to number 2. Same thing. So we compare. The first bit is 0 and 1, so that gives us a 0. The second bit is 0 and 1. It's still a 0. And then we have 2 zeros. They give us 0. And again, for this one, we'll have 1 and 1, which gives us exactly what we want, is 1. Then we have 1 and 0. We compare this one with this one. That equals 0. And then 0, 0. And if you see, as we test for the map, for that map over here, we're constantly alternating between we're all constantly alternating between 0 and 1. So for anyone who's doesn't use bitwise operators, because JavaScript, most people don't use bitwise. Like if you're a JavaScript developer, you're most likely going to use a modulus. You're going to do like n step modulus. I think is 1 or 2. I think it's 2. Then that alternates between 0 and 1. I keep forgetting. I always forget about modulus, but when it comes to bitwise operations, that's like, it's right there. It's just 0 and 1. Modulus is just a divisions thing. It just gives you a remainder of a division. So, and like I said, division is always slower than anything else. It's one of the slower operators for a CPU. So you are better off doing multiplication, and if you can do bitwise operations, that's probably even better, because now you're not even doing anything mathematical. Now you're just comparing binary. So for anyone who knows what bitwise operators and knows this trick, whatever, to alternate, sorry. But for anyone who's not, bitwise operations, I love them. They're fun to do. Binary is always fun. It's always good to know. So let's say, like I said, my end step. Just tell me if it's 0 or 1. Then I take the end step plus 1 and do it. So whatever the current step is, I'm just going to do plus 1, and I know what my moving in. So my pivot foot is always going to be whatever the step is, bitwise 1. So there we go. Now we need to do the alterations. So and we keep track of our pivot index up here. So in that class object. So if our pivot is not the same as the one we thought it was, that means we're switching our pivot foots. I mean, the cycle is done, so then we're not keeping track of the cycles or anything. We're kind of just doing. I know there's a design pattern name for this, or an operation, not a master detail, but I guess something. Master detail kind of does something similar, so it allows you to alternate between master and detail records. But we're just keeping track. Oh, sorry, I spit. So we're just going to keep track. So once we know that the foot has changed, we're going to do some things. So we're going to just set the final position of our pivot, because you got to remember, we're animating our foot, so we're never going to reach 1 perfectly. So the animation will never end perfectly. So right now we're going to make sure the foot that was moving is now where it needs to be at the very end of the cycle. So this way, once we have it in position of where it, like this is like where we're positioning it where it needs to be at the end of the cycle. Since we're on a new cycle, we need to kind of just fix that, because we never actually reach value of 1. We always get like 0.999 or something like that when we're going through our cycle. You never reach 1, really. Never. Very rarely, unless you're doing a certain type of animation, that you always hit 1. But if you're kind of like using sine waves and things, you'll never really hit the value of 1. You get close to a value of 1, you get close to a value of 0, but you never actually hit those two values. So we're doing the exact same thing we did here, but with I think just 1 or 2 less lines of code. So we got our pivot foot. We're gonna get the distance between the 2 feet. We're gonna normalize it. We rotate it, but this time we're not rotating it by step. We're gonna do the full rotation, the full 120 degrees. Then we scale it. Then we add our pivot foot, which is now our moving foot. Now we got to realize our moving foot was the pivot for the previous cycle. So that's why I'm saying, well, I'm using the M index value because in this new cycle, the move foot, it was the previous pivot. And then we set the height to 0 because the foot is now touching the floor, or should be touching the floor. And then we just copy the value. We update the pivot index value, so this way we know not to reset it anymore. Just let the cycle continue, and we're good to go. So now, you can see how the end effectors move. Yeah, I got a nice itch on my nose. So there you go. And you can see the colors change. So once the moving foot ends, it turns to red because now it becomes the pivot foot, and the other one just keeps going. And there you go. And that's really the gist of actually how to move the foot around. You just keep everything in the same distance, and just change the height, and just add the rotation. Like I said, it's moving. It's perfect. There we go. Beautiful. I like it. I'm happy. Can I apply IK to it yet? No, not yet. All right. So there we go. So we have the end effectors moving for our feet. So now we know where our feet are moving. So the next thing is we need to calculate our hip. We need to know where our hip is. And take a guess where our hip is going to be. Our hip is going to be in the center of wherever the feet are. So all you have to do. So once we know the two positions of our end effector, all we have to do is then find the midpoint of that, like that. Like just think of those 2 points as 2 ends of a segment, and all we want to do is find the midpoint of that segment, and that midpoint of that segment then becomes the starting point, at least the x and z values for our hip, because the hip still has the height of y, which is going to be alternating. All right, so let's see. We're going now to calculate our hip, and I think I can do some things. No, I took some things out. I'm not happy about that. Let's see what it looks like. Yeah, it's doing a lot of things. All right. I don't want to do this yet. I had some demo stuff here, and it looks like I got rid of it at some point when I was cleaning up the code. Very upset about that. Let's see. Try to take some. There you go. That's a lot better. And let's do that for now. So there you go. So that's the idea. So once we have the orange button, the orange dot is really where our hip is going to be. So you can see it always kind of stays in the middle. Ooh, always stays in the middle. There you go. Now you can kind of see it. Kind of always stays. And always rotates closer to the pivot foot, which makes sense because that's how your body's going to move. So the easiest way to do that is like I said, I'm using hip IK to store the position of our hip. The easiest way to do it is just to take, like I said, the 2 positions and do a lerp, and just get the halfway point. There's so many ways you can do it. You can. I don't know. There's so many ways to get the center of between 2 values. And the quickest and easiest way is just use the lerp function to go halfway point. So that gives us the halfway point. And then we apply, because like I said, we just want the x and z values, and then we're going to change the y. So the y right now, I set it up to the hip height. So that's the hip height that we set it up for, minus y. Now we want to kind of animate the hip. So we want the hip to kind of move up and down. And let's see. So we have our hip movement, And we have our steps. So we're kind of using the same thing as calculate feet, which I think I did over here. So I'm actually copying it. This isn't like perfectly optimized, because I'm like calling this function twice when I only need to read it once. When I made this example like a couple of months ago, I actually had everything saved as a state. So this way I can just call it once and then reuse it for the whole thing. But for this example, I wanted everything to be in little pieces. So like I said, this isn't like perfectly optimized either. There's like duplicated code. But just keep that in mind, that you don't need to do this for every function. You should really probably do it in the update function, save the state somewhere in your object, and then just reuse that value over and over again. So just so you're not doing all the math all over again repeatedly when there's no need to. Because you're doing all this IK stuff. Anything you can cut off might give you a couple of milliseconds here and there. And every little bit of milliseconds you can cut out eventually adds up. So I know some people don't like to optimize in the beginning. I tried to do half optimize, so, but in this case I didn't do a lot of too much optimizing. So okay, we want to move our Y position. So we know what our maximum, like I think I said it for 0.2. That's how much total movement we're going to do. And we're just going to take our step value. Again, we're going to just pass it into a sine wave. This time we're doing pi times 4, so that means we're doing full 360 twice, so we're doing 720. So we're cycling 4 times, and you'll see why. Because in this animation, he actually bobs up and down twice per cycle. If I do 2 pi times 2, it just bobs once per cycle. So we'll play around with that, and you can kind of see how it works. So it just step times pi times 4, plus 1 and minus 5. That's really just to because pi creates a value between -1 and 1, and plus 1 times plus 1 times 0.5, which is also division by 2. I'm actually remapping the value of -1 to 1 to a map of 0 and 1. So that's what this all googly-gop is. It's just remapping. In case you don't know what's going on with all this math. So, and do negative, because we're going in the negative direction, the maximum value. So once we have our maximum value, you can say this is how much we move from our max, and so now you can see the dot dips twice for every step we take. So 1, 2, 1, 2, 1, 2. It's like a dance. Like you get that 1, 2 step going. All right, and like I said, you can just change this to 2, and we're only going to do 1 bob per step. So 1. So yeah, it just goes up and down once. But like for the dancing, it actually helps going by 4. So you get the double bounce, because you kind of you're dancing, you're having fun, you're into it. All right, I'm into it. I love IK. I love graphics programming. This is awesome. All right, so now we're playing with our hips. So we got the hip movement, we got the hips, we got the feet, we got the hips, and we got the feet. All right, so now there's only one thing left to do. There's only one thing left to do. Now it's all about just applying it to the IK stuff. So let me just, the last thing we need to do, let me call apply, the apply function. Calculate feet, we're good to that. Calculate hip. All right, so the last thing we need to do, oh, actually, you know what? I totally forgot to do something. Oh yeah, I totally forgot to do something. We're not done with the hip. So the next thing we need to do, which is not visible until we can move the mesh around, is that we need to know where the forward direction is, because as the character is moving, we need to know where the forward direction is. So if with the forward direction, then we can then rotate the body exactly where it's supposed to be aiming to. So to actually get the direction, let's say we create a vector, we subtract the distance, or we subtract the distance of not the scratch of the distance. We what do you call it? We create the direction between the 1 foot to the other foot, and we always the exact same 2 feet. We don't need to know which one's pivoting or not. It's always from left foot to right foot. What is the direction from the left foot to right foot? Because if we alternate, then it becomes a problem. If we always make sure we do the exact same 2 feet in the exact same order, and it makes it super easy. Because in my previous version, I didn't do that, and finding direction was actually a lot more complicated. So if we just get rid of pivoting and moving now, just stick with the 2 from left to right, we're good to go. So from left to right foot, we want to know which direction. Essentially, that creates essentially an x-axis, right? Then all we got to do is our beautiful cross apply. And we used our up direction with the direction from the left foot to right foot, and that would then, so we have our x, and then we have our y, which then generates our forward direction. Done deal. So super easy to figure out the direction. And then I can just output the line, debug. Oh, am I updating the hip? Oh, because I did the apply. All right. Well, here you go. Whatever. So there you go. So once we know that forward direction, then it makes pretty easy to figure out a rotation for it. And there you go. And you can kind of see where the hip now is like bobbing up and down. And if you want, I can show you just with the 2 steps. So he's bobbing a little slower. So he's more mellow in this one. And I know it looks bad with the debug stuff there. Oh, the orange line. It's a funny line. It's just a line. If you see anything filthy about it, you just have a dirty mind. Okay? It's just a line. That orange is just a line. It just tells me the direction of the hip. That's all it does. It's not to insinuate anything. All right, so stop messing around. All right, so how long is this stupid video already? Ooh, 40 minutes, man. I'm sorry, guys. All right, let me stop clowning around and get straight to it. So, so now we got to do the apply, and then to figure out the rotation, I do very simple. I just take the forward direction and then give me the IK direction that I saved up here from the cross apply, and just do a rotate 2. So this way it just gives me a rotation from forward direction to whatever direction I'm currently at. So I'm not using the look at function at all. I'm just doing a complete rotation. Just a very simple rotation. And then I just update the rotation for the hip, and I update the position of the hip. And the last step is now we just need to apply the IK stuff. And this is the same IK stuff we've been doing for a while now. So I probably don't want to waste too much time with you guys. I'll just show you the code. We're using the lim solver. I think that was the previous video. So we're using the lim solver, which uses the aim solver and blah, blah, blah. That yakety schmackety. So it's the same basically kind of code. So we need to get the world position of the hip. Then this way we can then pass it over to our IK chain. So we have the world position, then we calculate the world position for the start of the chain, which would be the upper leg. Then we use those values to create our IK target. So we know the start of the line, the end of the line, because we know our foot, because we know our 2 end effectors. And so this way we create our IK target. If the distance is greater than or equal to the length of the chain, if it's less than or equal to, we're going to use our IK solver. If it's longer, then we're just going to use an aim. We're just going to keep the feet straight. And then we refresh, and there you go. And now you got the IK feet sticking to the ground. And it's no fun looking at a skeleton, so we're gonna go scroll right back up. We're gonna switch this value to a 7, so this way we enable the skin to load. And there we go. Look at that. We have a dancing Vegeta. Vegeta's starting to dance because Beerus is around. When Beerus is around, Vegeta's he acts a little bit different. Some would say he acts like a little bitch. But, Beerus is dangerous. So he doesn't want his family to be blown up. So you gotta do what you gotta do. He's a good dad. I'm in the camp of where I believe Vegeta's a good dad and Goku not so much. Vegeta's is the dad of the year when it comes to Dragon Ball Z. So so we got Vegeta dancing. So there you go. And there you go. This is the end of the first part. We got the hip moving, we got the feet moving. In the next video, we're going to work on bending the spine, and we're going to move the hands. The hands, we're going to start adding noise to it, so this way we can kind of make the hands moving more random. Because the feet right now are not random; they're kind of following a specific order. But like I said, the original Unity project did have a lot of that random elements built into the hip movement, a little bit to the feet movement, and a little bit to the feet rotation. You can add all that stuff later. But like I said, this part was actually really long and complicated. But like I said, adding that stuff is easy once you understand the basics of it. And as you can see, like I said, we created the end effectors, and we just figure out where we want the hip to be. And the hip always has to be kind of like be in the middle of the 2 feet. Try to move around and try to see if your hip doesn't really stay close to the middle of the most part, unless you really try to stretch out one leg, but then you kind of off balance, you might fall. So be careful if you're actually going to try. So let's see, this video is like 40 minutes long. I was kind of hoping to shoot for 30. So let me end this right now and set myself up for part 2. And I'm actually going to upload all this in one night. So, but I just want to have it 2 separate parts so you guys can kind of chill out and relax. Just watch one part and not stuck here for an hour and a half listening to me talk about this. Blah, blah, blah. Wasting too much time. See you guys in the next video.